Okay, so we're back, and it's a little bit more review. Maybe some of this is new stuff to you. I want to do a special talk about the chemistry of water, because the properties of water are, again, incredibly important to understanding just basic chemistry. And so that's what I'm talking about here. The behavior and properties of water influence many phenomena. It's an important component of chemistry, so we want to specifically talk about some of the properties of water very briefly. Okay, so there's many ways we can represent the structure of water. Here's just a couple of 3D model or just a regular molecular diagram. Of course, you all know it's H2O. What we're trying to show with these pictures, though, is that the H's are at an angle to each other, about 105 degrees, I want to say. And so when you think of oxygen binding two hydrogens, earlier we talked about carbon chemistry and kind of being in a chain or a line, but it's not like that. The two hydrogens bind to the oxygen, but they're not like apart from each other, they're at an angle to each other. And so this, again, gets back to my earlier theme. Very small changes or very small properties at the molecular level have huge implications at the functional level. And so just the fact that the water molecule is shaped in this way influences some of its properties. So for example, it gives it polarity, okay? And so remember that when the hydrogen and oxygen react, it's a covalent bond, it's a sharing of electrons, right? And so that electron goes around the hydrogen nucleus, and then around the oxygen nucleus, and then around the hydrogen nucleus, and then around the oxygen nucleus. And by doing so, it keeps those atoms bound together. However, it's not they don't share fairly, okay? It's not an equal sharing. In water, the electron, goes around the hydrogen atom, and then it goes around the oxygen atom a few times. And then it goes around the hydrogen atom. And then it goes around the oxygen atom a few times. The electrons spend more time around the oxygen than they do around the hydrogens. But since the water molecule is shaped like it is, to where the hydrogens are off on one end and the oxygen on the other end, that means the electrons spend more time on one end of the water molecule relative to the other end. And that is polarity. And so it means that the end with the oxygen tends to be a little bit more negative, have a slight negative charge, and the end toward the hydrogens has a slight positive charge. So just that little change in the shape of water gives water polarity, but that has a huge influence on its properties. Now, why do those electrons spend more time on the oxygen end, or spend more time around oxygen's nucleus? Again, this is, you can get into this more deeply in your chemistry classes, but basically oxygen really, really wants electrons. That's a very simplistic explanation, but it's a good enough one for us, right? It's very highly electronegative. Oxygen wants 2 electrons to fill out its outer shell, and so it has a very high affinity for electrons. This is a property of oxygen that we're going to see again and again and again. Oxygen really wants to grab electrons. And in this example, the net result is those electrons spend more time around the oxygen. That ends up giving water polarity. Now, one consequence of this polarity is you get something called hydrogen bonding. And so covalent bonding is within a molecule, right? It holds atoms together. Hydrogen bonding is between molecules. And so if you look at this example here, you've got several water molecules. Remember, each of those has a slightly negative end and a slightly positive end. Well, it's only natural that slightly negative end is going to be attracted to the slightly positive end of a different molecule. And since that positive end is caused by hydrogens, we call this hydrogen bonding. And so this is something that holds water molecules together. Now, it's not exclusive to water. Like, lots of molecules have a hydrogen bonding, and later when we talk about like proteins and DNA, we'll talk about hydrogen bonding. And in some of those molecules, it is sort of within the molecules, different parts of the molecule. But at any rate, the important thing to understand is because those hydrogens are a little bit positive and the oxygen here is a little bit more negative, that causes a slight attraction. And it's not a very strong bond. Covalent bonds are very strong. Hydrogen bonds are very weak and easily broken. But the sheer number of them often ends up being very significant. So it's like, a single thread is not very strong, but if you wrap a bunch of threads around something, then it becomes very strong. And so you get stuff like capillary action or surface tension, right? You see this water strider standing on the surface of the water. Well, why is that? Because those water molecules are attracted to each other, and so they don't come apart when you put a light weight on it like a water strider. It's a very important property of water. Okay, another property of water that we talk about a lot is something called specific heat. Before we talk about heat, let's talk about temperature. Okay, and so these are terms that you use all the time, but we need to define them a little more precisely. So when we talk about temperature, hot, cold, and we measure temperature, but what is temperature? If you ask a physicist or a chemist, what is temperature? It's the average kinetic energy of molecules. And so, of course, molecules are always moving. Even the most solid thing, the molecules are vibrating and they're moving, right? And if they're moving, they have kinetic energy. Kinetic energy is the energy of motion, right? So you take potential energy and you can convert it to kinetic energy. So something that's sitting still has potential energy, a rock at the top of a hill, and then when it starts to roll downhill, it converts that potential energy into kinetic energy. Molecules are always moving, so they have kinetic energy. If you measure the average kinetic energy of those moving molecules, that's what we call temperature. And so if you heat something up, you're adding energy, the molecules are moving more, they have more kinetic energy, the temperature goes up. And if they lose energy, they start to slow down, they have less kinetic energy, the temperature goes down. It's how much molecules are moving around. And so water, just like anything else, if you want to increase the temperature of water, you add energy. And that makes the molecules move around more, and the temperature goes up. It's that simple, right? But to make those water molecules move around more, you have to break these hydrogen bonds. And so you add energy, and the water molecules start vibrating more, but they don't really move much because the hydrogen bonds are holding them together. And so you add a little bit more energy, and they vibrate a little bit more, but the hydrogen bonds still holding together. To get them to actually start moving more, you got to break those hydrogen bonds, which requires energy to break those bonds. And since it takes a lot of energy to break those bonds, it takes a lot of energy to warm up water, to change the temperature of water. And that is what gives it the property we call specific heat. Specific heat is how much energy it takes to change the temperature of an object. You get something like metal, it has a very low specific heat. You don't have to add much energy at all and it gets very hot. So the example I always give is, take a pot, fill it with water, set it on the stove, turn the burner up high and count to 60, right? So count, get a big pile of water. Now don't do this, right? So I don't want anybody to burn, but you could do it, it'd be fun. But just, obviously it's a metaphor, I'm just talking here. But if you heat up that pot, after 60 seconds, you could stick your hand in the water and it still would be fine because you put a ton of energy in, but the temperature of the water hasn't changed. But after 60 seconds, if you lifted up the pot, would you touch the bottom of the pan? Absolutely not, because that metal pan is really hot. It didn't take much energy to change the temperature of the pan, but it takes a lot of energy to change the temperature of water. And that is the property of specific heat. How much energy it takes to change the temperature. Because you've got to break these hydrogen bonds to change the temperature of water, it has a very high specific heat. Of course, then, you know, you're familiar with this, right? If you're on the coast or somewhere, the temperature is more moderate because the oceans take a lot of energy before the water temperature changes and the air temperature changes, but then they also hold that energy. And so you don't get as radical swings in air temperature. It works in the other way too. And so if you want to change the energy, if you want to cool water down, you have to pull a tremendous amount of heat out of it. And so water does not change temperature very rapidly. And so again, if you're on the coast somewhere, that means that the air temperature does not change very rapidly. And so it's more moderate climate around large bodies of water. But bottom line is, it takes a lot of energy to heat up water, and to get water to cool down, you have to lose a lot of energy. And so at high temperatures, you know, those molecules are flying around. There's lots of space between them. But if you lose that kinetic energy at high temperature, you've got lots of kinetic energy, lots of movement. But if you lose that energy, then the molecules slow down and they can pack down tighter, and the water is cooler, but it's also more dense. Now, all molecules do this. This is not a property of water. When things are hot, they move a lot more. There's a lot more space between molecules. The density of molecules is lower. When things cool down, the molecules don't move as much, and so they can pack tighter, and the density gets higher. Water does this. Everything does this. But what's unique about water is that at very cold temperatures, the density decreases again. So most things, when they're hot, they have a low density. As they cool down, the density gets higher and higher and higher. They get more and more dense. The molecules get tighter and tighter together. But with water, when it cools down, the molecules start to pack closer together. It gets more and more dense. But then it starts to form this crystal lattice. Instead of the molecules, as they get colder, getting even tighter and tighter, they start to form these hydrogen bonds and they start to spread farther and farther apart. And so as water gets colder, it gets more dense, but then it starts to get less dense again. Of course, this is why ice floats, right? Ice is made of this crystal lattice of water molecules. And since there's all that extra space in that lattice, it has less density. If it has less density, it's going to float to the top. Okay, you say, well, okay, ice floats, big deal, what do I care? What do you mean, what do you care? If water doesn't do this, then lakes would freeze from the bottom up. Lakes would freeze solid all the time if ice didn't float. If lakes freeze solid, then evolution can't happen. Organisms can't evolve. You know, we all evolved in these wet environments. But if they froze from the bottom and froze solid, nothing could ever exist. So this is something that you just know and you take for granted, but it's a huge thing. Now, water is not the only molecule that does this. Other molecules do this, but it's not common, but it's definitely an important property of water. As it gets colder, it gets more dense to a point, and then it starts to form this crystal lattice that makes it less dense, which allows ice to float. Now, you know that water forms ice at 0 Celsius, and water boils at 100 Celsius, but its maximum density is at 4 Celsius. So as you cool water down at 4, it's as dense as it's going to get, but then if you cool it even more, it starts to form that crystal lattice and its density decreases, and so you can get ice. By the time you get down to 0 and you start to form ice, you've got that crystal lattice that's set up and it floats to the top. And that crystal lattice is formed of those hydrogen bonds. And again, hydrogen bonds by themselves are very weak, but lots of them become very powerful. And so you can get things like this exploded Coke can, or you get frost heave, and you can get damage to your house if it's not built properly. And so all these small water molecules forming that crystal lattice and those hydrogen bonds, there's so many of them, they can exert a tremendous force. And so, again, something you have to take into account, because the freezing and thawing can have a huge effect on things because of all this power. Okay, another thing about water, it's called the universal solvent. Recall that water has polarity. It's a polar molecule. Polar molecules do dissolve other polar molecules well. Like dissolves like is what they say in chemistry, okay? And lots of molecules have polarity. And so since water is also polar, water can dissolve lots of these other molecules. Now, I think later on we'll talk in more detail about what's it mean to dissolve something. You do something, you form what's called a hydration sphere. And so you've got this polar molecule, and that polar molecule, whatever it is, it's got a positive end and a negative end. Well, so does water have a positive end and a negative end. And so the negative end of the water will be attracted to the positive end of whatever molecule you're dissolving, and the positive end of the water will be attracted to the negative end of the polar molecule you're dissolving. And so it'll be, this polar molecule that you're trying to dissolve will be surrounded by all these water molecules. That's called a hydration sphere, and that's what it means to dissolve. Then that molecule is isolated from other molecules. But it only works on polar molecules because water is polar, like dissolves like. What doesn't dissolve well in water? Well, oil, all right? Oil and water don't mix. And so you can infer from that things like oil, hydrocarbons, they're not polar. That's a non-polar molecule. The water can't form that hydration sphere, and so they don't mix well. And so here is an example of those hydration shells that I'm showing you. And so we're looking at dissolving a salt block. And so the salt is made of sodium and chloride, right? And those sodium and chlorides, now this is a little bit different than a polar molecule. They're disassociating. Instead of staying together and making a polar molecule, they're actually breaking into separate ions, but it's the same concept. You've got these positive sodium ions, these negative chloride ions, but since the water has both a positive end and a negative end, the water will interact with both of these. The water will interact with the positive ion and will also interact with the negative ion and surround them and keep them from each other. And that means then the salt is dissolved in the water. So look closely at this image that I'm showing you in the PowerPoint here, and look at how those water molecules are oriented, right? So you've got that negative chloride ion. The water molecules have their positive, their hydrogen end, tucked in next to it. Then if you look at the positive sodium ion, the other end, the negative end of the water, the oxygen end of the water, is what's interacting with that. But because water has both those ends, it can do this with no matter what the charge, and it can form this hydration shell, and you can dissolve things. And again, it's just an important aspect of water that influences its properties and its chemistry. Now, in this example, we're dissolving salt. And so you can see how all those salt ions, when they get dissolved, they're surrounded by water molecules. Those water molecules are associating with the salt ions and not with each other. And so if the water molecules are they're hydrogen bonding to the salt molecules, then they can't hydrogen bond to one another. If they can't hydrogen bond to one another, they can't form that crystal lattice that happens when it gets really cold. And so this is why salt lowers the freezing temperature of water. This is why you can put salt on the road or salt on your sidewalk in winter and you melt the ice, because those salt ions grab the water molecules so they can't link arms with each other. If they're allowed to link arms with each other, they'll form that crystal lattice, which makes ice, which is slick, and you fall on your butt. But if the salt gets in there, it disrupts that crystal lattice. The salt is grabbing arms with the water molecules. They can't grab arms with each other, and so even though it's getting colder, they're not forming that crystal lattice. So again, just understanding a little bit about the shape and the properties of water, you start to understand other phenomena. Okay, last thing I want to talk about is dissociation of water. Water breaking into pieces. And so pretend you had a beaker of pure water, distilled, deionized water. You put it in a beaker. It's nothing but H2O molecules. If you do nothing to it, if you just put that water in a beaker, some of those water molecules will spontaneously break apart. This is just another property of water. And so some of those water molecules will break into a hydrogen ion, which is this H plus I'm showing you here, and a hydroxyl ion, which is OH minus. Now you might remember hydroxyl from an earlier lecture when I talked about functional groups, right? I said it's a hydroxyl group, OH. When you hear a hydroxyl, think OH, okay? The OH, the hydroxyl group, has a negative charge. The hydrogen ion has a positive charge. So again, you don't have to do anything to the water. The water will just break apart on its own. And when it does that, there's an unequal sharing of electrons. And so the oxygen always likes electrons, right? So the oxygen is going to get an extra electron. That's why that hydroxyl has a negative charge. And so then the hydrogen ion is left without an electron. And so some of the water molecules will just do this. And now, it's just like any other chemistry, it's back and forth. So some will break apart and they'll go back together. They'll break apart, go back together. And so this one will break apart and then come back together, but this one over here will break apart and go back together. So it's just a constant thing, right? But it's always happening, and it's happening spontaneously. Now remember, when we talk about hydrogen, it's very simple. A hydrogen atom is just a proton and an electron. Here we've got a hydrogen ion, which is a hydrogen that's lost its electron. Well, it only had one, and it's only a proton and an electron. Anyway, a hydrogen ion is just a single naked proton. And so again, just to kind of show you this, here's a typical hydrogen atom. You got one proton, no neutrons, one electron circling it. That's a typical hydrogen atom. If you strip it of that electron, then all you're left with is a proton. And so when we talk about hydrogen ions, it's the exact same thing as a proton, and we'll use those interchangeably, all right? But what do we know about protons? Protons have a positive charge. Here we've got a single proton all by itself, nothing else, and so hydrogen ions have a positive charge. And remember, we say that water will break apart, and it will break apart into hydrogen ions and hydroxyl ions. And this is what I said earlier. When they break apart, because oxygen really likes electrons, it will take the electron with it, and it will steal that electron. So the hydroxyl now has an extra electron and a negative charge. The hydrogen ion is just a naked proton. It has a positive charge. Now, a neat property of water is we know exactly how many water molecules will break apart like this, okay? And so if I've got a liter of water, 1 times 10 to the negative 7 moles of water will break apart like this in that liter. So it doesn't matter how much water you've got, it's always a known concentration. And so pure water at 25 Celsius, 1 times 10 to the negative 7 moles per liter will spontaneously break apart into two pieces. Just a property of water. At any time, a certain concentration of water molecules will break apart. Like I said, eventually they'll come back together, but a different one will break apart. And it'll reach this equilibrium where just a certain small number of them are just going to spontaneously break apart. Well, this is a property of water that is very, very important to chemistry. And we want to measure how many of these water molecules break apart by measuring how many hydrogen ions you have. And so every time a water molecule breaks apart, you have one naked hydrogen ion. And so if you measure the concentration of hydrogen ions, that tells you how many water molecules break apart. But this is an important concept in chemistry called pH. And you've heard of pH before. I'm sure you've seen this. This is probably a review for you, but I'm going to go over it again. pH is the negative base 10 log of the concentration of hydrogen ions in moles per liter. And so all that is represented by this first bullet here, right? And so in pure water, we know that 1 times 10 to the negative 7 moles per liter of water will spontaneously break apart. That means that in pure water, you're going to have 1 times 10 to the negative 7 moles per liter of hydrogen ions, because they came from those water molecules that broke apart. And so the pH, this formula I'm given here, is just a way to easily handle those numbers. That's all it is. It's nothing, there's nothing complex about it. It's just a way to take these, 1 times 10 to the negative 7 is just a big cumbersome scientific notation number. All we're trying to do is reduce that to a simpler number that we can talk about easier. That's all we're doing with this formula. And so let's take that 1 times 10 to the negative 7 moles per liter and plug it in to the formula that I've given you here. And so the pH is the negative base 10 log of 1 times 10 to the negative 7. Well, 1 times 10 to the negative 7 is just the same thing as 10 to the negative 7, right? So I can simplify this a little bit. So the pH of pure water is the negative base 10 log of 10 to the negative 7. Okay, so let's review what base 10 logs are. Go back to your algebra. Remember that base 10 logs, it's just an easy way to do math, okay? That's why base 10 logs were invented. You can do things a little bit easier if you're in base 10. But the big picture is, remember that base 10 log of x equals y. That means if you take 10 and raise it to the y, it equals x. And so, again, by switching things to base 10, it's just an easy way to work with exponents and things like that. It's the opposite of an exponent. And so in our example, we're saying the base 10 log of 10 to the minus 7. That's part of our formula, right? So that if the base 10 log of 10 to the minus 7 equals y, which we don't know, that means 10 to the y equals 10 to the negative 7. Well, you can just compare both sides of that equation there. You can see, oh, y must equal negative 7, right? So just review logs again. Big picture, what that means is we can plug that into this formula, and that's how we can convert this concentration of hydrogen ions, which is kind of a large, a cumbersome number, into a simpler number, right? And so in pure water, the concentration of hydrogen ions is 1 times 10 to the negative 7 moles per liter. And so when we plug it into the formula, we want the pH is equal to the negative base 10 log of 10 to the negative 7. We just showed that the base 10 log of 10 to the negative 7 is negative 7, right? Because we're raising 10 to the negative 7. But pH is the negative of that. So we want the negative of negative 7, which is positive 7. Confused yet? Don't worry about it. Study it. It makes sense. You've seen this before. But don't forget why we're going to all this trouble. All we're trying to do is take these concentrations of hydrogen ions that we have to express in a cumbersome scientific notation, because that's their value. We just want to convert that to a number that's easier to write, easier to talk about, easier to explain. That's all this is, right? Now, if you recall, when we talk about pH, as the number of hydrogen ions goes up, that means you're more acidic, but the pH goes down. As the number of hydrogen ions goes down, you become more basic and the pH goes up. And so, you know, that's always something that you have to remember when you talk about pH, is that it's a little counterintuitive. As pH goes down, the acidity goes up, the hydrogen ions go up, but it's because you're taking a negative of a negative, right? So, for example, let's say that we've got that pure water and we dump some acid in. We add some hydrogen ions. So now our concentration of hydrogen ions is 1 times 10 to the negative 4 moles per liter. Well, 1 times 10 to the negative 4 is actually a bigger number than 1 times 10 to the negative 7, right? Because we're working with negatives. We're on the right side of the zero. That's why this works backwards. That's the only reason. It's not a huge deal. And so, again, we plug that in. The pH is the negative base 10 log of the concentration of hydrogen ions. We just said the concentration of hydrogen ions is 10 to the negative 4 moles. So we want the base 10 log of 10 to the negative 4 is negative 4. We want the negative of negative 4, that's 4. So the concentration of hydrogen ions went up, but the pH went down. And that's just how it works. It's no big deal. The important thing is that you realize where these numbers come from. And don't forget that we're talking about the pH, and the H in pH is hydrogen ions. Bottom line, if I give you a concentration of hydrogen ions, you can give me the pH, and vice versa. You should be able to do that. It should be just second nature to you. As things become more acidic, as hydrogen ions go up, pH goes down. Each 1 unit change in pH means a 10 times change in the acidity, or a 10 times change in the hydrogen ions. So for example, if we have a solution at pH of 4, that's 1,000 times more acidic. And that's another important thing. Because it's on a logarithmic scale, it's on a base 10 scale, 1 change in pH is actually 10 times change in the concentration of hydrogen ions. And so when you go from 7 to 6, you've got 10 times as many hydrogen ions. When you go from 6 to 5, you've got 10 times as many hydrogen ions. When you go from 5 to 4, you got 10 times as many hydrogen ions. So when you go from 7 to 4, you've got 10 times 10 times 10, 1,000 times more hydrogen ions, or 10 to the third more hydrogen ions. So, you know, pH changes very quickly with each unit change in pH. So you've seen this before, you're familiar with pH. It's very important, but hopefully now you understand why pH of 7 is considered neutral. That's because water spontaneously breaks into hydrogen ions and hydroxyl ions, but we know exactly how many do this. 10 times 10 to the negative 7 moles per liter. But why should we care so much about pH? Why do we make such a big deal? pH tells you how many hydrogen ions are around, right? So the lower the pH, the more hydrogen ions. Hydrogen ions are just naked protons. The thing is, those hydrogen ions are very reactive, and they're very common. So consequently, no matter what the chemical reaction, they're always sticking their nose in. No matter where you're at, there's always hydrogen ions laying around. And since they're so reactive, they have a tremendous influence on other chemical reactions. And so we always worry about pH, because pH influences lots of other chemical reactions just because of their ubiquity. All right? For example, you know, you've got a low pH in your stomach, right? Your stomach is very acidic. Well, that helps, those hydrogen ions attack, they're so reactive, they attack food molecules and they start to break them apart. You start to have those chemical reactions in your stomach that break that food apart because you've got so many hydrogen ions that are beating on those molecules. But if those hydrogen ions get, up into your esophagus, then they also will attack nerves and tissue in your esophagus, and it hurts and you get heartburn. If that pH gets down into your intestine, if that low pH, if those hydrogen ions get down into your intestine, they can attack your intestine. They can interfere with the enzymes that help to digest and take up food. The pH in your garden influences how many nutrients are available. pH is everywhere, and it's the reason we worry about it is because it's measuring those very reactive hydrogen ions, and there's so many of them, they always have an influence on chemistry. So, there you go. That's why we worry about pH, and you're going to see pH a lot all semester. Okay, and so those are some of the most important properties of water. And let me know if you got any questions, but that's all I have for this topic, and I will see you later.